So now that you've had a chance to read a little bit about what mutations are and what kind of mutations can occur and what the consequences of them can be, let's take a look at the mechanics of it a little bit. This is a simulation that I uploaded for you. It's part of a worksheet that at the top you click it open and you get this. You don't need to do the worksheet. I'm not grading it, okay? I just wanted you to have an example that you can manipulate to kind of play with what mutations will do and what they look like and where they happen, okay? So I don't want you to worry about turning that worksheet in, but it's there for you to take a look and study how this works. The real work is going to be that HHMI activity that I'm going to put you into groups and you're going to start that. That's going to give you lots of mutation examples. So if you look at this, this is kind of nice because it takes us back to the beginning of the unit where it shows DNA and it shows transcription and translation. So let's look at transcription and translation just as if there were no mutations, right? So without mutations, here's an RNA molecule being made. It doesn't show the RNA polymerase doing it, but you can see how it's going one by one and adding complementary RNA nucleotides to the open DNA strand. There it is. Okay. So there's transcription. Translation is going to happen outside the cytoplasm. That brown thing is the ribosome. And then each green transfer RNA comes in with its anticodon, meets up with the codon on the red RNA. And there's a growing polypeptide here, right, with amino acids that are coded for by the messenger RNA codons. These three codons here are what you look for in the chart to get each amino acid one by one into a chain. And then this is the final protein. And this is what the protein looks like when everything's fine, there's no mutations. So now let's reset it for a minute and take a look at what would happen with certain types of mutations. So one of the mutations that you read about in the mini lesson was this one. What if I did that? You saw what I did right there. What kind of mutation is that? Can you chat me the answer? What kind of mutation is it when that's a substitution, yes. That is an example of a point mutation that's called a substitution. I changed that C out for an A. Okay, so what kind of change would that cause in the final polypeptide? What could that one nucleotide-based substitution cause? It could cause, it might, yes, in the case of the hemoglobin gene, that's exactly what it does. That is, yeah, it might cause the wrong amino acid. Yes, that is absolutely right. Both of those answers are correct. Yes. So generally, this is the least harmful type of mutation. Exchanging one nucleotide for another can be the least harmful. It might change a single amino acid, or it might not even change it at all. If you noticed that the chart that leads from the codons to the amino acids, there's some redundancy in that chart. So if you change one letter, you might still get the same amino acid there. That's called a silent mutation. So that can happen too. So the substitution mutation can cause harm because that's actually what causes anemia, but it's potentially the least harmful. Okay, what if, on the other hand, I did this? What kind of mutation is that? That is a deletion. Excellent. Now what would that cause in terms of the amino acid sequence coming from this? Something that starts with an F that you read about just now. If I delete one nucleotide base, what that causes is every codon, every group of 3 codons after that deletion is going to be read incorrectly. So every amino acid then after that deletion is going to be the wrong one because it's reading in groups of 3, right? So that causes something called a frame shift. If you delete a letter, then the RNA polymerase is just going to go on. The transfer RNAs are coming and recognizing every 3 codons gets an amino acid. It's going to be recognizing the wrong codons after that deletion. That's called a frame shift. that can be potentially very detrimental. Frameshift mutations are caused by either a deletion or, what if I did this? Or a deletion causes a frameshift, but so does an insertion. Excellent. Yes, that's it. So if I add a base, it's just as bad. Now I've also changed the amino acids following that insertion or deletion. And both of those result in a frame shift of the reading of the codons, meaning that every single amino acid after that point is the wrong one. That can severely change the final protein. Most frameshift mutations are lethal. I mean, depending where they are, they can be lethal. So if you actually show the final protein for that, you get actually a different protein than the original one, if you look at it. I don't know if you remember what the original one looked like, but it'd be totally different. So it would not perform the same function because you know that proteins rely on their three-dimensional shape to do the right function. Okay, let's reset again. Now, what if I did this? What did I just do? Yes, Elsa's right, way ahead of it. Excellent. Okay, so I deleted 3 bases, which is actually much less harmful than just deleting 1. Because when I deleted 1, it caused a frame shift of everything following it. So everything amino acid after that single deletion was wrong. But now if I delete 3, I'm eliminating an entire codon. So that only changes a single amino acid. The protein might still be okay without that one amino acid. It just depends where it is, right? If it's a really important one, like if it's right in the active site of an enzyme, you might have a problem. But if it's buried somewhere else in the protein that's not a real functional part of the protein, you might be all right. Okay, so that's all I wanted to say about that. And I think now what I'm going to do, let's see,